Hello everyone, my name is Anatoliy Rozanov. I'm software developer in Intel MPI, and my colleagues Dmitry, Durnov and Michael Steyer with me. This agenda for the webinar. The first topic is an overview of GPU programming model. After that, I would like to tell you about two features in Intel MPI, which can help you to simplify programming for Intel GPUs. These are GPU pinning and GPU buffer support. Then I would like to show you a short demo, and then we will have time for your questions. Few words about GPU programming model. MPI primitives can be used for communications between GPUs. The argument for the most of MPI primitives is just a pointer to some memory, and this memory could be allocated on GPU. So you can work with MPI as before with host buffers, but now the buffer is just GPU buffer. And we can identify two types of MPIs. These are host-centric MPI and GPU-centric MPI. In host-centric MPI, operations with GPU is initiated from the host. It can be some communication between GPUs on the same node or on different nodes, for example, pipelining or DMABUF, direct GPU memory access, or it could be local GPU to GPU communication. Also, it can be some kernels for collective operations. For example, MPI can compute reduction for MPI reduce and MPI reduce on GPU. And all these operations can be initiated from the host. So you still call MPI primitive from the process on CPU, and the primitive is running on the CPU. But there is some synchronization with GPU, and there is some overhead to start operations on GPU. And another type is GPU-centric MPI, where operations with GPU are initiated from GPU kernel. With this model, you can call MPI primitives from GPU kernel. And where is Intel MPI now? Now Intel MPI is host-centric GPU-aware MPI. There is support of GPU buffers, and now we are working on performance optimizations such as pipelining and reduced GPU kernel, and some other optimizations in later releases. And the next step for us is going from host-centric MPI to GPU-centric MPI to be able to call MPI primitives from GPU kernel. But currently we are host-centric MPI. Another aspect of programming model is resource manager. So there is different GPU configurations you can face with multiple GPUs on the host. Each GPU can have multiple tiles, one tile, or even does not have tiles, and you should somehow handle it if you want to use all available resources on the machine. It may require manually run domain decomposition or use some explicit scaling mechanism, which is not always desirable. And another aspect is efficient sending data between different GPUs. This GPU can be located on the same host or on different hosts, and you need different optimizations to support these cases. So, and how Intel MPI can help here? Intel MPI enables single tile or GPU programming. It means that you need just to focus on a single tile and leave everything else to MPI library. Intel MPI can assign GPU devices to individual MPI ranks. Means that Intel MPI means that on different GPU systems, Intel MPI can help you to run one tile per rank or one rank per tile, and you need to run as many ranks as tile you have on the machine, and your application will use all available resources. And after that, you need somehow to communicate between ranks. And another feature can help here. As I said before on previous slide, Intel MPI is GPU-aware MPI now. It means that there is ability to pass GPU memory pointer to every MPI primitive. For example, MPI send or MPI receive. If you want just to send data from one GPU to another GPU, this GPU can be located on the same host or on different hosts, it doesn't matter. And you can also call some collective operation like MPI all reduce to involve a set of GPUs and do some reduction. Okay, let's start with the first feature, Intel MPI GPU pinning. Intel MPI can automatically distribute GPU devices between MPI ranks. It means that after GPU pinning, each MPI rank will see only some of subset of all available devices. For example, only one tile. So no user code changes required on different GPU configurations. You need just to run as many ranks as tile you have. The feature is NUMA-aware. It means that GPU pinning takes into account on which NUMA node and the GPUs and ranks are located. And we use level 0 library inside MPI to distribute resources between ranks. The feature is disabled by default. To enable it, you need to set MPI offload top leaf variable equals level 0. And there is a set of variables to control pinning behavior. This variable starts with MPI float prefix, and you can find default settings on this slide. In the next slides, I will show examples for all these variables, just to understand how the pinning works and how you can change behavior of the pinning. Okay, the first example. All examples represents machine topology with 2 NUMA nodes, 2 GPUs, and 4 tiles. 1 GPU per NUMA node and 2 tiles per GPU. You can find this configuration in the picture. There are 2 NUMA nodes, 2 GPUs. Each GPU is split into 2 tiles. And also, you can find on the picture on which NUMA node each rank is located. For example, in this case, we have 4 ranks, and first 2 ranks are located on the first NUMA node, and other 2 ranks are located on the second NUMA node. This is responsibility of our another feature, CPU pinning. So Intel MPI can distribute on which CPUs the rank will be running. So for now, 2 ranks for each NUMA node. And so the rank is still running on the CPU. It's important. So and you can find result of GPU pinning inside tiles. These ranks are ranks for which the tile is visible after GPU pinning. So in this case, GPU pinning will pin 1 rank per tile. So because we have 4 tiles here and 4 ranks. So only 1 tile will be visible for the rank. You can also find the result of GPU pinning in our debug output. If you set MPI debug equals 120, then it will show how Intel MPI identified GPU topology. You will see it for each host. You can find here how many normal nodes, GPUs, and tiles on the machine, and GPU placement. It shows on which normal node, GPU, tiles, and ranks allocated. So here we have one GPU on one normal node per one normal node, and 2 ranks per normal node. And if you set MPI debug equals 3 or higher, then you will see results of GPU pinning. Here you can find which tiles are visible for the rank after pinning. And as you can see, 1 tile per rank in this case. And tiles enumeration is consistent. It means that, for example, the tile with number 3 here is the second tile of the second GPU, or the last tile in the picture. So the next example. Here's example when the number of tiles is more than the number of ranks. Here we have 3 ranks. And in this case, some of the ranks will have more tiles than other ranks. For example, in the first picture, only rank with number 2 is located on normal node 1. That's why 2 tiles will be visible for this rank. There is a variable that controls how many tiles will be visible for the rank. It's domain size, MPI float domain size variable. The default value is after. With this value, domain size can be different for each rank in order to use all available resources. And in the second picture, only rank 0 is located on the first normal node. That's why 2 tiles will be visible for this rank. And 1 tile will be visible for the rank 1 and 1 tile for the rank 2. So I would like to say that the result of GPU pinning depends on which normal node ranks allocated, ranks and GPUs. So here you can see the difference. So another variable, MPI float cell. This variable controls what base unit is used in pinning. The default value is tile, but you can change it to device. And full device with all tiles on the device will be visible for the rank. For example, like here, full device will be visible for full first device will be visible for rank 0 and rank 1, and full second device, full second GPU will be visible for rank 2 and number 3. This variable affects all other variables. For example, when I said about domain size variable, I said that that variable controls how many tiles are visible for the rank, but it's more correct to say that that variable controls how many base units will be visible for the rank. And the same for other variables. Okay, next slide. Another example for domain size variable. Now it's not after value. It equals 1, which means 1 tile per rank, because cell is tile. And you can see that each rank will have only 1 tile, and the last tile is not used here. So your application will not be able to run to compute something called communicate with the last tile. So each rank will see only 1 device, which is tile. MPI float devices variable. This variable controls which devices are available for pinning. By default, all devices are available, but you can disable for some reason some of devices. The device here is full GPU with all tiles, so you cannot disable one of tile, just full GPU. And in this example, I disable the second GPU, GPU number 1, and only GPU 0 is available for pinning, and only tiles from this GPU will be visible for the ranks. So here we can see oversubscription when several ranks share the same tile, the same device. And there is ability for custom pinning. You may set distribution. You may set every distribution you want using MPI float domain variable. For that, you need to set. You need to create bit masks for each rank, separated by comma. This bit mask you should reverse and then convert to hex numbers. And already converted hex numbers you need to provide to this variable. 0 in bit mask means that the tile with its index is not available for the rank, and 1 means that the rank is available. The tile is available for the rank. For example, for the rank 0, we have mask 1101, and it means that all tiles will be visible for the rank 0 except the tile with number 2, and you can see it on the picture. So we can see rank 0 except this tile. For the rank with number 1, only tile with number 1 is available after pinning, and you can see it in the picture. So and so on for another ranks. So you can set every distribution you want if other variables cannot set this distribution. So that's all about GPU pinning feature. In summary, this feature can help you automatically distribute GPU devices between MPI ranks, which gives you ability to support different GPU configurations without code changes. And the next feature is GPU buffer support. So this feature gives you ability to pass MPI, to pass GPU, to pass pointer to GPU memory to every MPI primitive. For example, MPI send, MPI receive, MPI backcast, or MPI all reduce, and so on. Of course, you can copy your GPU memory to host and provide a pointer to host memory to MPI primitive like before, but it's not efficient because you need to wait this copy from GPU to host or from host to GPU, and Intel MPI can optimize this path. Also, MPI ranks can be located on different hosts or on one host, on the same host, and you need and different performance optimizations are needed for to support these cases, and you can leave this responsibility to Intel MPI. Currently, we are working on these optimizations, performance optimizations, but the functionality is already in the library, and currently we support OpenMP and DPC++ USM pointers, so we can already pass to Intel MPI USM pointers, or for example from level 0. By default, this feature is also disabled. You need to set an MPI float variable to enable it. And in the next slides, I will show you how to get that USM pointer from OpenMP. So here's example without this feature. it's how you can work with GPU if MPI is not GPU aware. So we have OpenMP code, which computes something on GPU. In the first pragma, we specify rules for mapping. Here we can specify what we want copy to GPU and what we want to copy from GPU to host. Also, we have our array values, and we need to copy this array to GPU at the start of pragma and copy this array from GPU to host at the end of the pragma, because after that we want to send this memory to another rank. Inside pragma, we compute something on GPU in for loop. For that, we specify pragma MP target parallel 4. So we change our memory here. Values is pointer to GPU memory, and this all compute on GPU. And after that, we want to send this data to another rank. Here is communication is on CPU, and values is pointer to CPU buffer. So in this case, you need to wait copy from GPU to host if you want to send it, if you want to use MPI to send data to another rank. And this is example with GPU buffer support. As you can see, MPI send here is inside the pragma, but it's still communicated on CPU. Then array values is copied only to GPU. We don't need to copy it from GPU to the host. And we need to say to OpenMP use device pointer in the first pragma and is device pointer for the second pragma. And after that, all pointers to values here is pointers to GPU memory, to device memory. So here is again compute on GPU, and MPI send is communicate on CPU. But now we provide a pointer to values, and MPI can optimize this communication. And another rank should just call MPI receive to send this data. This rank can be located on another node, for example, or on the same node. And technically, you can specify receive buffer can be host buffer or GPU buffer. So you can copy from GPU on one rank to host to another rank, or to GPU on another rank. So here is command line how you can compile your application with offload, OpenMP, and MPI. Command lines for C and Fortran languages, and command line how to execute your application. Do not forget to specify MPI float variable to enable GPU buffer support feature, and specify MPI float topalib equals level 0 variable if you want to distribute GPU resources between MPI ranks. So in conclusion, there are two features in Intel MPI which can help you to simplify programming for Intel GPUs. GPU pinning does not require code changes, and you can already use it if your code can work with one device. And another feature, GPU buffer support, requires some code changes, but it can optimize your code with future Intel MPI releases. And on all information from the slides you can find in our documentation. Please find developer reference for Linux, and there find GPU support page. And now I would like to show you a short demo just to show how command lines and output from MPI looks like. and just show some examples for GPU pinning. I will run the same example from the slides that open MP code on which one rank communicates something on GPU and then send data to another rank. Okay, let's start. Okay, at the start I need to source compiler and MPI from one API package. Here I compile my example. And let's check GPU buffer support feature. I set MPI float variable equals 1. So I run 2 ranks. After initialization, the rank with number 0 waiting data from rank with number 1. At the same time, the rank with number 1 computes something on GPU, and after that, send data. You can see that we send GPU memory by its pointer. And after that, the rank with number 0 received data and validated it. So GPU buffer support works. And now let's check GPU pinning. I set MPI float tapalib variable equals level 0. And I would like to show you GPU configurations. I set MPI debug equals 120 and run for ranks. This debug level generates a lot of output, so I use grep to decrease the output to show only relevant output for us. And for each host, you will see GPU topology from Intel MPI. Here you can find how many NUMA nodes, GPU, and tiles on the machine. So we have 2 NUMA nodes and 2 tiles, like in the slides. Then you can see GPU placement, on which NUMA node GPU tiles and ranks are located. And then we can see the result of GPU pinning. In this case, we have 1 tile per rank, because we have 4 ranks and 4 tiles. Also, you can find at the end result of CPU pinning. You can use this information to understand on which NUMA nodes the rank is located. We print this information with MPI debug equals 4, so it you don't need to set 120 to understand on which NUMA node the rank is located. Now I will leave only results of GPU pinning. I set MPI debug equals 3. And let's check the results with 3 ranks. So like on slides, the last rank will have 2 tiles because only this rank is located on the second NUMA node, and other ranks will have only 1 tile. So now I will set MPI float domain size variable equals 1. So, and you can see only 1 tile will be visible for the ranks. Each rank will have 1 tile, and the last tile is not used in this launch. Okay, let's set MPI float cell variable equals device. So after that, full device with all tiles on the device will be visible for the ranks, and you can see that first 2 ranks share the first device, full first device, and full second device is available for the rank with number 2. Okay, let's set one more variable MPI float devices. I would like to disable the second device. So only device with number 0 is available, and we can see it in the results. Only first device is available for pinning, and we have third device and only one device available, so all ranks will use only this device. So you can combine different variables and we'll see different behavior. And if it's not enough for these variables, you can set custom pinning, MPI float domain variable, specify hex numbers, which will be converted to bit masks inside MPI, and it also works. Those 3 tiles will be visible for the rank 0, mostly all tiles except the tile with number 2. Only one tile will be visible for rank with number 1, and 2 tiles for rank with number 2 and with number 3. Okay, that's all. Thank you for attending the webinar, and now we have time for your questions.
Thank you, Anatoly, for your presentation. We have the speakers online, and if you have any questions, you can either put that in the chat box or in the questions box, or you can raise your hand and I can unmute you and you can ask the question yourself. So we had a question from Pratik. He's left, but he was asking, what do you mean by all reduced GPU kernel? So I think this question was, is there an implementation for GPU? I think is what he was asking.
We can compute reduction for all reduce and for MPI reduce on GPU. So we can compute the sum, for example, on the GPU and reduce copy, the size of copy of the array. So before, okay, yeah.
Yeah, I just want to clarify the main idea behind that approach is that we try to minimize the amount of data to move through PCIe or any kind of bottlenecks like network. So when we have technical data on 2 tiles inside single GPU and we perform a reduce or reduce operation, we can reduce operation inside GPU first on GPU buffers, and in that way we simply just halving the amount of data we will have to pass through the PCIe. And as a next step, if we have multiple GPU on a single node and we perform operation across the multiple GPUs, we can just divide the amount of data to be passed to the network by the amount of GPUs. So that's the way we do that in a hierarchical manner, and the way we minimize amount of data to be sent through any kind of links slower bandwidth than local communication would be able to provide.
Mm-hmm. Yeah. Okay, thank you. Any other questions? I don't have, I don't see anything in the chat box yet. Let's give the, okay. Can you post the documentation link in the chat? That's a question from Jerome.
Okay, I will share. Give me a minute.
That'd be great. Any other questions in the meantime? Okay. Okay, I'll read the next question while you post the documentation link. So the next question from Jerry is, at an abstraction level, is the tile comparable to a streaming multiprocessor, an SM? And any plans for MPI to target SMs for other type of GPUs from NVIDIA or AMD?
I think that I may reply to that question. So first of all, the tile here is kind of close to NUMA domain. So we have the lower level possibility to go to the low level, and the lower level access is available to the let's say DPC++ programmer, and that's explicitly available there. Right now, we support on 2 levels. So we support device level and tile level, and we analyze the way how we may expose lower level entities. That's an answer to the first part of the question. And the second question regarding support of other vendors is that we are analyzing the way we could add that, because we see that there were several requests for the functionality. Right now, it's not clear to what degree the support will provide. I mean, what kind of features we will be able to map. But we are going to address that based on our customers' request, and if there will be demand and the functionality, we will definitely consider that.
And if I may add here, Dmitry, comparing so you cannot compare tile basically to a streaming unit, because a tile is more like a complete GPU itself, if you want, right? And you can combine multiple tiles to a larger GPU. So basically, a tile then has slices and sub-slices, and then eventually execution units within the sub-slice. So it's really a hierarchy of parallels.
Yeah, and tile it's like a normal domain, like multi-socket machine. I mean, in that sense. So you may think that you have socket, a normal node with multiple cores, and here we have GPU with the multiple tiles. That's kind of the highest level of the access. And as Michael mentioned, it's like a whole GPU.
Okay. Next question is, can an IPC handle to USM or device memory be obtained and available to user?
Technically, you can use level 0 to get direct access to all the mechanisms we employ. But the idea here is that you won't have to do that. You simply pass pointers to the memory you worked with, to MPI runtime, and MPI runtime will handle that IPC handles exchange inside the MPI runtime, and it will expose the memory across multiple processes, and it will open them, so it will get the handle, perform the handle exchange, and it will expose that, so everyone will see the memory, and it will do the work for you. But if you wish to do that yourself and implement some logic which will work with IPC handles directly, you can work with abstractions provided by level 0, like it's the lowest level API. But in our current approach, we definitely recommend kind of abstract that and make MPI the layer which will be responsible for organization of that communication between the tiles or between GPUs. But the answer is that technically you may organize a portion of the communication yourself. Yes, it's possible.
Okay. Any other questions? I think we've covered everything from the chat window. Let's give folks a minute to see if they have any other questions. Looks like not. Well, then let's move on and thank our speakers one more time. Thank you so much for coming in and speaking. I think this is a very relevant topic for our community, especially with the offerings we'll have soon. And I'm sure there's a lot, this is fairly important, and there's a lot that we can do with this. So thank you so much. For all the attendees, this webinar has been recorded, and the recording link and the link to the slides will be sent out to you in an email shortly, once we have it available on our website. And thank you so much for attending and participating in the webinar.
Thank you.
Thank you.
Thank you.